Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Izan Haikal bin Zaman Hui and my matrix number is 23119395. Okay, this topic is talking about the Regnault Transport Theorem, or known as RTT. Okay. What is the Reynolds Transport Theorem, RTT? RTT is a relationship between the time rate of change of an extensive property within a control volume and the flux of that property across the control surface. It is widely used in fluid mechanics to analyze control volumes. RTT can bridge the description of a system all following a fluid particle and a control volume or fixed region in space in fluid mechanics. So, RTT is important to engineer because the engineer can analyze and design systems such as pipe, turbine, and pumps. So before the know the equation of RTT, just know the basic concept RTT. Basic concept RTT has two, extensive property and intensive property. What is the meaning of two of them? So extensive property is a property that depends on the system size or mass. For example, mass, momentum, energy. So the symbol is B. Second is the basic concept RTT is a intensive property. Intensive property is the property per unit mass relate to the extensive property as formula B equals to B over M. Intensive property B for small alpha. So B small equals to B alpha over M. M is mass. So RTT is a relationship between the system versus control volume. So system versus control volume. A system consists of a fixed mass of fluid, and a control volume is a fixed region in space through which fluid may flow. So the RTT helps to connect the analysis between these two properties. So it is the relationship system and control volume. So you can see the figure 455 is relationship system and control volume. The RTT provides a link between the system approach and the control volume approach. Okay, it is the system and control volume. So in the right side is about the moving of the control system. So it is about a moving system, harsh region, and a fixed control volume or shaded region in a diverging function of a flow field at time t and t plus rate of change of t. The upper and lower bounds are streamlines of the flow. So the green is the green in the left is inflow during rate of change of t. So in the outside no color is the outflow during the rate of change of t. So the control volume at time t plus rate of change t is the green for the line green. So the system material volume and control volume at time t shaded again in the green for of if flow during t. So the system at time t plus the rate of change t h region is the middle. So green has the many lines is here. So it is how to moving system and a fixed control volume in the figure. Okay, back to equation. How to establish equation RTT? So I will simplify. So let me represent any extensive properties such as mass, energy, or momentum, and let B equals to B over M represent the corresponding intensive property. Nothing the extensive properties are additive. The extensive property B of the system at time t and t plus the rate of change of t is expressed by as B system t equals to B contour volume t. Next B, and so I will skip. So the taking the limit as rate of change t to 0 and using the definition of derivative, we get dB system over dt equals dB contour volume over dt minus B in plus B out. So you can see if, the figure for 438 is the equation. So it states that the time rate of change of the property B of the system is equal to the time rate of change of B of the contour volume plus the next flux of B out of the contour volume by mass causing the contour surface. This is the desired relation since it relates the change of a property of a system to the change of that property for a contour volume. Okay, so in the right side, is for example for the other formula, for figure for 39 about inflow if negative. So the 440 is about the total amount of property B within the contour volume must be defined by integration. Is B contour value equals to integrate CB. Rho B dV. Rho is the density. V2A is specific volume. So for is for figure 440. So is figure 441 is about the RTT phase of CV. So the RTT, also known as the system to contour volume transformation for all phase contour volume, dV system over dt equals dV dt, and so on. So next is the equation of 442 is the alternate from the Reynolds transport theorem. For phase contour volume is dV over dt equals to plus integrate P rho V B times and dA. So it is about the general case of all moving and all the forming contour volume. Okay, next. Okay, in the equation for 43 is a relative velocity. It's about the absolute fluid velocity V in the last term is replaced by the relative velocity. So the next, where VCS is the local velocity of the contour surface. The most general form of the Reynolds transport theorem is thus dV over dt equals to d per dt integrate CV rho B dV plus integrate CS rho BV and dA. See the figure equation of 444 is about RTT non-phase contour volume. Okay, so the equation of 445 only is about the alternate RTT and non-phase contour volume. Application of the Leibniz theorem, it can be shown the Reynolds transport theorem for a general moving or deforming contour volume is equivalent to the form given by this question, which repeat here. Okay, I am read the 445. So you can see is the alternate RTT non-phase CV. So during steady flow, the amount of the property B within the contour volume remains constant as time, and thus the time derivative becomes 0. The RTT reduced to dB system over dt equals integrate rho BV and the equation of 446. Okay. Okay, so the approach mentioned in this equation is that when property B is uniform over cross section area A, so A is becomes dB SYS over dt equals d by dt integrate CV PV dV plus the sum of M mass flow rate B minus mass flow rate B average. So it is for 47. So the final solution is in some application we may wish to rewrite in terms of volume greater than mass flow rate. In such case, we make a further approximation that mass flow rate equals to rho average specific volume equals to rho V average A. This approximation is exact when fluid density rho is uniform over A. So it become dB SYS over dt equals d over dt integrate CV rho B dV plus the sum of rho BVA minus the sum of rho BVA. So it is simplified for each outlet minus for each inlet. It is approximate altitude for well-defined inlets and outlet. Okay, in the figure, an example control in which there is one well-defined inlet and two well-defined outlet 2 and 3. In such case, the control surface integral in the altitude can be more conveniently written in terms of the average value of fluid properties considered as inlet and outlet. It is about the equation for before. So 1 and 2 well-defined outlets. So 1 is inlet and outlet is 2 and 3. So this is my explanation about altitude and establish of the equation. Thus I have developed the altitude. So thank you.